All right, well, welcome back to Calculus 2. So today is going to be our final day talking about series in any form, power or otherwise. And then starting on Monday, we're going to get to the final part of the class, which is going to be talking about different coordinate systems, which will be immensely helpful if you guys choose to go on to Calculus 3. All right, so what I want to do is I want to start off today what I wanted to end class with last time. I think in the chat a few weeks ago, we were kind of cryptically mentioning that somehow the sum of all the whole numbers, or the positive whole numbers, so if we keep adding them like this, it ends up being negative 1/12 somehow. The mic is bad. Why is the mic always bad? Like right when I start. Okay, there we go. All right, so I want to give an explanation as to where this comes from and what the deal with this is. Is the sum of the positive numbers really somehow negative 1/12? What's the deal with this? So what I'm going to do is I'm going to start by calling the sum, whatever number it is, I'm going to call it S. So S is equal to the sum. And my goal is to compute what number S has to be right here. Okay, now what I'm going to do is I'm going to, from this, subtract 4 times S. So what does negative 4 times S mean? Well, what I do is I just multiply all of the whole numbers by negative 4. So I would have 1 times negative 4 would be negative 4. 2 times negative 4 will be negative 8. 3 times negative 4 would be negative 12. And that would continue on forever as well. All right, so what I'm doing is I'm taking away 4 times the sum from all of this. What's the name of this lesson? Oh, this is actually from the last lesson. This is lesson 28 right now. This is the part we didn't get to last time. Okay, now what I'm going to do, I'm going to do S minus 4S, and I kind of wrote it like this to suggest how I'm going to do that. So I do S minus 4S, well, that's going to be negative 3S. And I have 1, I don't really have anything under that, so I'm just going to have 1. And then I have 2 minus 4 is negative 2. I have 3, and then there's nothing under that, so it's going to be plus 3. I have 4 minus 8S, so it'll be minus 4. And I add 5 here, 6 minus 12 will be negative 6, and so on. Why are we subtracting? You'll see in a bit. I'm just trying to compute what S is, where S is the sum of all these whole numbers. All right, now we can write this as a series. We can write this as the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n. Now, why is it negative 1 to the n plus 1? Well, it seems like the negatives are on all of the even numbers. So in order to get that to happen, I write that as negative 1 to the n plus 1. So that's what this series is right here, and this is negative 3s. Okay, now I'm going to put this on hold for a minute. I'm going to come back to it later. Now, what I'm going to do next seems seemingly unrelated, but it's going to tie together into this. First, I want to find the series for 1 over 1 plus x. Well, this is 1 over 1 minus negative x, right? So this is the sum from n equals 0 to infinity of negative 1 to the n, x to the n. So I think we've seen this series before, 1 over 1 plus x. Now, what I'm going to do is I'm going to take the derivative of this. So I'm going to do the derivative of both sides here. The derivative of 1 over 1 plus x, if I use the power rule, will be negative 1 over 1 plus x squared. Meanwhile, over here, if I do the power rule on this series, I raise my index because I do a derivative here. I have negative 1 to the n, and I bring my n down. I have x to the n minus 1. And then finally, what I'm going to do is I'm going to multiply both sides by negative 1. So negative 1 times negative 1 will be positive 1. And multiplying by another negative 1 over here will be negative 1 to the n plus 1. Okay. Now, you might be able to see where I'm going with this now. We just got this series, and earlier we had this series right here. So these will end up being exactly the same if I use what x value. What x value should I plug in for those to be the same? Well, if I plug in 0, then the whole thing will end up being 0 right there. Yeah, so we're going to plug in 1 for this because 1 raised to any power will just be 1. So I'm going to plug in x equals 1. So I have 1 over 1 plus 1 squared is the sum from n equals 1 to infinity, negative 1 to the n plus 1 times n, and then 1 to the n minus 1 is just 1 right here. Okay, so that means that this right here is 1 over 1 plus 1 squared, aka 1/4. But this series right here is identical to the one that we found up here. So now it's time to make our conclusion here. So negative 3s is n equals 1 to infinity of negative 1 to the n plus 1 times n is equal to, and then we saw in this side of things, 1/4. So remember, what is my goal ultimately? My goal is to compute what s is going to be. So now I have a very simple equation for s. I have, just a second. I have negative 3s is 1/4. So if I divide by 3, I get that s ends up being negative 1/12. And that's where all of this comes from. That's why people say, oh, the sum of the whole numbers is going to end up being negative 1/12. And so there's a proof of it. Now, as it turns out, there's actually some mistakes we made along the way here. It turns out that no, the sum of the whole numbers is not actually going to be negative 1/12. What are some, do you guys spot any of the mistakes that we made through this process? What's one mistake that won't quite work? What was one thing we weren't allowed to do that we did? Minus 3s. Yeah, so that's an interesting thing here. So we're subtracting 4 times s here. So we have all this, and then s is 1 plus all these numbers right here. So what we're doing is we're combining these two divergent series together. And these are divergent because they fail the test for divergence. So we're subtracting these divergent series, and then we come up with something else. But you're not allowed to combine two different divergent series like that because they're not really numbers like these. Yeah, you can't really do that here. There's another mistake that we made a little bit later on. Does anyone see what that mistake was? X equals 1. That's right. If we look up what the interval of convergence for this series is, it's negative 1 to 1, but it doesn't include the 1 right there. So we're not allowed to plug in x equals 1 into this series right here. So that was another mistake that we made. We can't actually put 1 in here and then get 1/4. Equivalently, in addition to this not making sense that it's negative 1/12, it also doesn't make sense that this ends up being 1/4. That also doesn't really work here. So there are definitely some flaws in this reasoning, but it's kind of like a fun math trick that you can show people. All right, so that's one bad thing we can do with series. If we abuse series as power, we can do something like this. Let's talk about some more productive things that we can do with series here. And this is going to be our next lesson here. Lesson 29. Taylor and Maclaurin series 3. All right, so what we're going to do two kind of interesting applications of series, one of which is going to help us compute limits, and then the other one is going to help us compute derivatives. So example 1, use Maclaurin series to evaluate the limit as x goes to 0 of e to the x cubed minus 1 minus x cubed over x to the 6th. Okay, now whenever we see a limit, our kind of gut response is let's just try to plug in the number. Let's just see if that works. Maybe we'll get lucky. So we put 0 in here. We have e to the 0 is 1. 1 minus 1 is 0. And I subtract another 0. But then on the bottom, I have 0 as well. So this is a 0 over 0 limit. Okay, well, if we have a 0 over 0 limit, we're tempted to use L'Hopital's rule. But the thing is that if we start using L'Hopital's rule, it's going to take 6 derivatives before this gets to something that's not 0. Meaning we have to do 6 derivatives of our top as well. And especially doing 6 derivatives of this will not be very pleasant. So sometimes while you can use L'Hopital's rule, it's not really in your best interest to do so. Well, what are we supposed to do instead? Well, this is where series can help us out. What I'm going to do is I'm going to find a Maclaurin series for e to the x cubed. Well, if we remember from before, we know a good Maclaurin series for e to the x. It's x to the n over n factorial. So that means it's relatively straightforward to find a Maclaurin series for e to the x cubed. It's going to be x to the 3n over n factorial. All right, now what I'm going to do is I'm going to write out the first few terms of this. So if I plug in n equals 0, I have x to the 0 over 0 factorial, that'll be 1. Then I plug in n equals 1, I have x cubed over 1 factorial, so that's x cubed. I plug in 2, I have x to the 6th over 2 factorial. I plug in n equals 3, I have x to the 9th over 3 factorial. And that would continue on forever with that. All right, so what I'm going to do is I'm going to take my series and I'm going to substitute it in to my limit here. So another way of writing this limit is 1 plus x cubed plus x to the 6th over 2 factorial plus x to the 9th over 3 factorial, and so on. And then after all of that, I'm going to subtract 1 and x cubed. And then we can't forget I'm dividing by x to the 6th down here. Okay, now why did I do that? That just seemed like it made things a lot worse. Well, there's 2 things that end up getting better here. We have a 1 here and a negative 1 here. So those will cancel out. And then we have an x cubed and a negative x cubed there. So those will cancel out as well. So we have the limit as x goes to 0 of x to the 6th over 2 factorial, x to the 9th over 3 factorial, and then a bunch of other stuff. All that's divided by x to the 6th. All right, now we notice that every single term remaining at this point has at least an x to the 6th in it. So what we could do is we could divide all of these ones up here by x to the 6th. So if we do that, x to the 6th over x to the 6th here will just give me 1 over 2 factorial. X to the 9th over x to the 6th will give me x cubed over 3 factorial. And then if I wrote the next one, this would be x to the 12th over 4 factorial. Now it's x to the 6th over 4 factorial. Okay, well, I still have this series. I still have the limit. What's going to happen next? Well, now it's actually safe to plug in 0, because the whole thing preventing us from plugging in 0 earlier was that we were dividing by it right here. But now we're no longer dividing by 0. And we have a 0 here, we have a 0 here, so these are all going to 0. As is the rest of all of these terms, they have x's in them. But we're still left with this 1 over 2 factorial. And that's going to end up being our limit, because even if x goes to 0, this is going to remain right there, because it doesn't have any x's. So this procedure, even though it kind of seems a little unwieldy at first, it's definitely faster than doing 6 derivatives of e to the x cubed. I probably still would have been doing that by now if I chose to do it that way. So you can use Maclaurin series to help you solve difficult limits. So now you might be like, okay, well, I'm willing to grind through 6 derivatives if it means I don't have to use series. But I've put on exams before where it's like x to the 100 or something. So like there will be times where you can't just grind through all of that. All right, so why don't you guys give this a shot? I'll give you a very similar problem here. All right, use series to evaluate the limit as x goes to 0 of sine of x minus x plus 1/6 x cubed over x to the 5th. So go ahead and give this a shot. Okay, show the top page a little more again. Oh yeah, I forgot to give this one for sine. So sine of x is the sum from n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Yeah, that's right. I keep forgetting to give them to you now. Yeah, that's right. Yeah, so yeah, there's a formula sheet in the file section of Canvas. I'm going to post it in the miscellaneous section relatively soon, so you can see what series you're going to get on the midterm 3 and the final. All right, I'll give you another minute or two here, and then we'll go over. Do they have 1 over 120 as an option? Uh-oh. Okay, it should be 1 over 120. Maybe the quiz is broken. Okay, let's go over this. Let's see if it's 120. Maybe we're all wrong. Maybe it's something else. All right. So let's see here. So we want to use this series to help us do this limit. So what we're going to do, we're going to write out the first few terms of this series, and that's going to give us x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. All right, so I'm going to substitute that in for my limit. All right, and that goes on forever. We have minus x plus 1/6 x cubed, all of which is divided by x to the 5th. All right. So let's see here. We have an x minus x. Those will cancel. 3 factorial is the same as 6, so those will cancel. And then everything left over has at least an x to the 5th in it, right? So I have x to the 5th, x to the 5th, x to the 7th. The next one would be x to the 9th, and so on. So we could divide by x to the 5th here. So x to the 5th over x to the 5th will leave us with 1 over 5 factorial. And then we have x to the 7th over x to the 5th, which will leave us with x squared over 7 factorial. If we were to write the next one, we'd have x to the 4th over 9 factorial. Well, it'll be a minus next, and then et cetera. And if we send all of these to 0, all of these terms with x in there will go to 0, and we just end up with 1 over 5 factorial, which apparently isn't an answer. Did it have like 1/5 or something? Maybe I forgot to type in the exclamation point. Or is this one that you need to type in the answer? 1/6, 1/24. Oh, geez. Okay. Well, sorry about that. It really is 1 over 5 factorial. I guess you guys will get a freebie on this quiz. All right. Anyways, let's move on. So that's how you can use series to find limits here. And we can also use series to help us compute large numbers of derivatives. Well, how do I get rid of the x to the 5th in the denominator? I'm doing all of the stuff in the numerator divided by x to the 5th. So x to the 5th over x to the 5th, those will cancel. X to the 7th over x to the 5th will leave us with x squared. And there's an x to the 9th and an x to the 11th in there, and that would leave us with this stuff right here. All right. Let's see. So our next example. All right. So what I want to do for this example, and this is another one that you could technically do the old-fashioned way here, but it's not advisable to do so. What I want to do is I want to find the 60th derivative at 0 if f of x is e to the x cubed. So I want to take that function that I used in my first example, I want to take 60 derivatives of it, plug in 0, and see what number I get. All right. Now, that we could definitely do this in Calc 1, but it would take a really long time, especially since we're going to start getting product rules off of this. So how are we really supposed to do this? Well, we're going to end up using series to help us. So we already saw what the series for this was. We used it for an earlier problem. E to the x cubed is the sum from 0 to infinity of x to the 3n over n factorial. Now, I want to pay attention to the thing that's next to the x here, right? So the coefficient of each of these is 1 over n factorial right here. So that's the coefficient of this. Now, remember, we have a nice formula for our Taylor coefficients. We have that the mth derivative at 0 over m factorial is a sub m, where a sub m is the number next to x to the m right here. So that means that in this problem, if we want to know what the 60th derivative at 0 is, we would plug 60 into here, and then we have 60 factorial is a sub 60. And this is the number next to x to the 60. Now I made a point of writing a different letter than this. So I have n's as my variable here. I wrote m's here. And that's because m doesn't necessarily need to be the same number as n. N is just the index for the series. M is the power that we care about right here. So I want to find what the number next to x to the 60th is in my series. And then if I multiply both sides by this factorial, I have 60 factorial times a sub 60. That will be my derivative right here. Where did I get this equation? This is the equation for Taylor coefficients. This is how we find our Taylor coefficients. All right, so let's see here. Now I want my x to be to the 60th power, right? So what does that mean that my n is going to end up equaling here? What n is going to provide me with x to the 60th here? It's going to be 20. That's right. Okay, so if I'm plugging in n equals 20 into this, and that gives me x to the 60, I'm also plugging n equals 20 into this. So that means that my a sub 60 will be 1 over 20 factorial. That's going to be the number that's next to x to the 60th here. So I take this, I put it into my equation here, and that gives me that my derivative, my 60th derivative at 0, is 60 factorial times 1 over 20 factorial. And there we go. I was able to compute my 60th derivative in the time it maybe took to do like, I don't know, like 4 or 5 of those derivatives right there. Yeah, what's up? Because the number next to x to the 60th happens when I plug in n equals 20. So if I plug 20 in here, I have 3 times 20 is 60, and the number next to that will be 1 over 20 factorial. Right there. That's the number that's next to x to the 60th. Why does n equal 20? Because it's the number it's the index that gives us x to the 60th power. Because we care specifically about what number is next to x to this power. We don't care what index it is. We just want this to match the power and the number of derivatives that we do. All right, so why don't you guys give this a shot here? This time, let's up the ante a bit, or let's practice 2. This time I want you to find the 100th derivative at 0 if f of x equals arctangent of x. All right, so, and then the series for arctangent of x is the sum from n equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1, right here. Where'd the 60 factorial come from? Yeah, it came from this m factorial here. So we have 60 factorial divided, or our derivative divided by 60 factorial, and we just bring that up here. Now think carefully about this one. This one's a little bit different from the example I did, but it's the same principle. Is the derivative equation a standard? If you're talking about this is just the general formula for Taylor coefficients. It doesn't have anything to do with this specific function. This is how we get the numbers next to our x to the powers for our Taylor series. When we make those tables, we're really figuring out what these are. That's right. Yeah, that's how we were able to get our derivative. Because normally we want to figure these out and we know what the derivative is. This time it's backwards. We want to figure out the derivative and we know what the coefficient is. Do we exclude the alternator? No, that's going to be incorporated into this. You can include the alternator. Like I said, think carefully about this one. No, you don't exclude the alternator. You include that. So this would be your coefficient. Is then 99 over 2. Wait, why was 60 factorial m factorial? Because we wanted the 60th derivative. So we plug in 60 for this factorial as well. You guys another minute or so, and then we'll talk about this one. This one's kind of interesting. Yeah, people could keep getting n is 99 over 2. But think carefully about that. Does that make sense? You're on the right track. That's the right way of thinking. All right, let's take a look at this. Let's see what's going on here. So in this problem, we want to find the 100th derivative of this function at 0 right here. So according to the Taylor coefficient formula, the 100th derivative at 0 divided by 100 factorial is a sub 100. And remember what this number is. This is the coefficient of x to the 100 in our series, right? So whatever this number is, it's the number that's next to x to the 100 here. Okay, well, let's find out what n value makes our x be 100. So we set this equal to 100 here. So the index we're looking for, 2n plus 1, has to be 100. 2n is going to be 99. So it seems like our index has to be 99 over 2. But there's a problem with this. When we go through all of the n values in our series here, when we plug in all these n values, what do all these n values have in common? They're all what type of numbers? Yeah, they're all integers, right? Now, does 2 go evenly into 99? No, it doesn't. So this isn't an integer. So that means that the only possible index that could have made this 100 is something that we're going to skip over anyways. So let me kind of explain what's happening here. If I were to write out all of the terms in this series, let's see. I would have, so I'd have a bunch of stuff earlier, and then I would have 1 over, let's see, 97, x to the 97, minus x to the 99th over 99, plus x to the 101 over 101, minus x to the 103 over 103. We see that the 2n plus 1 here, 2n plus 1 is always an odd number. So there's never going to be a time, if we plug in whole numbers, where that's going to give us 100. Now, our goal is to know what happens inside here. What number is next to x to the 100? Now, traditionally with polynomials, if you don't have x to a power, then what is the coefficient of that x to a power? It's 0, right? So we can imagine that in between all these odd numbers, we may have something like plus 0 times x to the 98th, and then plus 0 times x to the 100. It's the only coefficient that it could be because we don't have it at all. It needs to not be there. So our coefficient, our a sub 100, is actually going to end up being 0 right here. So we end up with 0 on this side of our equation. We do 0 times 100 factorial, and I don't care how big 100 factorial is, times 0, it's not going to be anything. So that means that our 100th derivative is going to be 0. Now, let me tell you this. If you manually grinded out 100 derivative of this and then you get 0, you'd be extremely disappointed. So it's best to do these problems not taking the derivative manually. Please don't try to do that. Every year, there's always someone, at least when we did the written test, there was always someone that just really tried to do like 100 derivatives or whatever. But yeah, don't do that. Okay, so how did I get 0? So I'm looking for the n value that needs to make 2n plus 1 into 100. But when I solved for that n value, I found out that it wasn't a whole number. But the problem is that n can only be a whole number. When it goes through 0 to infinity, we only go through the whole numbers. So that means that there's not going to be an index here that's going to give us x to the 100. And this is what it actually looks like. If we start going to powers close to that, we have x to the 97 over 97 minus x to the 99 over 99, and then we skip 100 and go x to the 101 over 101, and so on. Now, if we ever are missing a coefficient, then, or we're missing an x to a power, that coefficient is going to be 0. And Joshua sums it up really nicely here. So if our desired value is ever not an integer, then the answer is going to be 0, and that's right. So if n is not an integer, then the derivative will be 0, because the coefficient of that missing term needs to be 0. Otherwise, if it wasn't 0, it would be there. So our coefficient needs to be 0, and then 0 times whatever factorial it is will give us 0 right here. What do we do with the part of the arctan series that we circled again? Well, if we did get a whole number, then we would plug that whole number into this. So if like 99 over 2 was a whole number, we would plug that in here, see what this is, and then it would go right here. All right, so there we go. There's another example of that. Now, for the last part of class here, I want to just show you something really cool that we can do with series. And this is probably my favorite part of the class here. This is my favorite part teaching it, and it's also my favorite part when I took Calc 2 way back when. Now, I just want to advertise this. This isn't going to be on the exam or anything. This is just a really interesting application of series I think everyone should see who takes this class. Okay, so what we're going to do is we're going to look at something called Euler's formula right here. Now, Euler's, first of all, this word is pronounced Euler, like it's like oil, or if you want to piss off a math person really fast, say it's Euler or something. They'll always get mad. So this is Euler's formula. So before I say what the formula is, I'm actually going to reveal what the formula is once we get there. What I'm first going to do is I'm going to start off by reminding us that e to the x as a series is x to the n over n factorial right here. All right, so we have that. Now, what I'm going to do is I'm going to do something a little bit strange. What I'm going to do is I'm going to put the imaginary unit number I as a coefficient. Now, as we saw when we put other coefficients there, what we do is we put them also to the nth power. So if I substitute an I in there, then I'm going to have ix to the n. And then this is 0 to infinity. We have I raised to the nth power, x raised to the nth power. Okay, now what I'm going to do is I'm going to write out the first few terms of this series right here. All right, let's check out what n equals 0 is. Well, I have I to the 0. Well, any number to the 0, including I, is going to be 1. X to the 0 is 1. N factorial is 1. Or 0 factorial is 1. Of 1. All right, next, I have n equals 1. I to the first power is I. And then I have x to the first power is x. And I divide by 1 factorial. All right, now here's where things get interesting. I'm going to go to n equals 2. I squared, what's that going to be? Well, the whole definition of I is that when we square it, we get -1, right? So if I do I squared, that's going to result in a minus sign. And then I have x squared over 2 factorial. I'm going to do this for a few more terms until we see the pattern here. So we have n equals 3. Well, if I squared is -1, then if I multiply both sides by I cubed is -I. So I'm going to have a minus, and then I'm going to have a single I, and then I'm going to have x cubed over 3 factorial. All right, now let's see what n equals 4 is going to give us. Well, I kind of already spoiled it. If I multiply both sides of this by I have I to the 4th is -I times I. So I'm multiplying both sides by an I right here. But then I times I is -1, right? So I end up with 1. So if I squared is -1, I could also imagine this, I'm squaring both sides, and I have I to the 4th is +1. So I'm just going to have +1, which doesn't show up. I have x to the 4th over 4 factorial. Now it seems like we've come full circle. I to the 4th is 1. So if I multiply both sides of that by I to the 5th is I. So it seems like every 4 powers, I is going to cycle back around. So my next one is I to the 5th, which is also just I. I to the 6th will be the same as 4 powers before it, which is I squared. And at this point, I think we have enough here to illustrate what I'm about to do. So this is what's coming up next is the cool part. So I have e to the ix, right? It was equal to all this stuff. Now what I'm going to do is I'm going to divide this between the i's and the non-i's. So the things that don't have i's in it are 1, -x squared over 2 factorial, positive x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, so on. So I'm going to group all those together. And this goes on forever. Next, I'm going to group everything with i's together. So I'm going to factor out an I here, since they all have it in common. And then I have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And that would continue on forever as well. Okay. Now, I know we don't encourage you guys to just straight up memorize the series, but I think we may have written these down enough to where these might seem familiar. Does anyone know what this is as a series? What function does this represent right here? Does anyone recognize what this is? This is cosine, right? It's cosine because it only has even terms. Remember, cosine is the sum from n equals 0 to infinity, -1 to the nx to the 2n over 2n factorial. It's the one that alternates and only has even terms. Okay, and then we have plus I. And then does anyone recognize what this is? This one only has odd terms and it's alternating and it divides by the factorials. This one's going to be sine of x. And here we go. This is what I was trying to prove. It turns out that e to the ix is equal to cosine of x plus I times sine of x. And this right here is Euler's formula. So what makes this so interesting, in addition to having an imaginary number, that's definitely going to spice things up, is that we're relating an exponential function to sines and cosines. So sines and cosines as functions, they only go between -1 and 1, right? Whereas the exponential function, that can get as big as you want. So it's very bizarre to have them related together in a formula, at least at first, until you start understanding what I is actually doing here. But there's also something else that's really cool about this. So what I'm going to do is this works for any x, right? The interval and the interval of convergence for all of the series that we just looked at was all real numbers. So I can plug in any x value and this formula will still work. So that's another nice thing. What I'm going to do is I'm going to plug in x equals pi into this. So if I plug that in here, I have e to the I pi, and then I have cosine of pi plus I times sine of pi. All right, well, we know our unit circle values. Cosine of pi is -1. And sine of pi, that's going to be 0. So we lose our imaginary component right here. Then what I'm going to do finally is I'm going to add 1 to both sides. And then we end up with this very kind of aesthetically pleasing formula that e to the I pi plus 1 equals 0. Now, if you had to list probably the 5 most foundational numbers, the most important numbers in mathematics, these 5 would be it. And miraculously, they're related together in one single equation right here. So this is kind of a special case of Euler's formula, and this is probably one of my favorite equations in math. It kind of just ties everything together, e I pi of 1 and 0. All of these numbers show up in many different fields of math, and they're all related together in one equation here. Now, like I said, you don't need to memorize this proof or anything for the exam or anything like that. For those of you who take DiffyQ, you will actually be using this formula. So it's not totally esoteric or out there. This is used to solve differential equations, which are very practical. But we're not going to be dealing with this for the rest of the class here. I just kind of wanted to show you one thing that we could do with series. So this is really foundation of a lot of stuff in math. All right. Anyways, that's it for today. And that's actually it for series as well. So when we come back on Monday, we're going to start something called parametric equations, which will be immensely useful for those of you going on to Calculus 3. So see you then. I hope you all have a good weekend.